All right, how's it going, AS Chemistry? This is a little video for you on your study guide to help you guys through it, to give you guys some assistance, and help you in studying for this celebration of learning. So I made this study guide for you guys. I posted it on Canvas, and yeah, just going to walk you guys through it. So do note that these equations are the 7 equations I'm going to give you on the celebration of learning, and so this is what you will be given. And then I've put some questions here on some various topics that will be covered on your celebration of learning. And so let's go through this one by one. The first topic, of course, is the first one that we learned, KMT, right? And I already went through this because it was some drawings and I didn't want to bore you by having you watch me draw. But basically, first thing to consider is what is the definition of KMT? KMT is kinetic molecular theory, which simply says that matter is made of particles. Now I've underlined that for good reason. That's the core of it, right? The matter is made of particles, these little dots, these little circles that we've been drawing, okay? So matter is made of particles, and second off, the other point is that particles are always moving, and we represent that movement either via arrows or vibrations if the vibration is, or sorry, if the matter is in the solid state, right? We show that the particles are only vibrating in place. All right, so that's what kinetic molecular theory says, and so to answer these questions, right, you want to use the word particles, right? Really and truly, a good explanation of any phenomenon probably on this celebration of learning is going to use the word particles. If you are explaining something for this celebration of learning, use the word particles, please. I can't tell you how many of you didn't use the word particles either on your KMT kind of final product that we made, or on the 2.1 to 2.3, did I get it? Please, particles. Use the word particles, okay? That's what KMT is all about. So here, where it says explain the ball and ring demo, when we heat the ball, why is it no longer able to fit into the hole? You remember this, so we saw it, and so the question is, why did that happen? Why did the ball expand? And what we can see here is that the ball is made of particles, right? So I drew some particles and I showed them vibrating in place with these little quotation marks. This is the before. Now, after we heat it up, what we see is that, we still have the same sized particles, okay? So the size of the particles doesn't change. The mass doesn't change either. We don't have more particles. And sorry, so I shouldn't have done that. I'm sorry, I put 9 here. There should be, if there's 9 there, there should also be 9 before, okay? So we're not gonna change the number of particles, right? All that's changing is how far apart these particles are. Before they were more condensed together, now they're gonna be further apart. The reason for that is because when we heated the ball, the particles gained energy and thus moved around more, right? If you gain energy, you're gonna start moving around more. This word kinetic energy, right, referring to the amount of movement, right? So if you gain energy, you're gaining really kinetic energy, and therefore you're going to be moving around more. And when you move around more, when the particles move around more, they're going to go further apart. That molecular, what's happening molecularly, right, the particles moving around more, going further apart, is going to result at the macroscopic level in the ball expanding, okay? And so molecularly what's happening is the particles are gaining energy, moving around more, and therefore going further apart. That the result of that is the ball is going to expand. Okay, and so if you draw something like this with particles and you show the movement with either arrows or quotation marks here because it's solid, right? Show them going further apart, then talk about particles. You'll do well on these type of questions, okay? And so similar thing here, right? I actually pulled this from the 4th period. Did I get it, right? It's the same idea that 4th period had for there, did I get it? Why does the liquid inside of a thermometer rise when the temperature increases, right? It's the same idea. The particles gain energy, move around more, and thus go further apart, resulting in the liquid expanding out and going higher, right? And so same idea, right? I don't want to bore you by jotting it all down, but right, same idea. Use the word particles, talk about how they move further apart. All right, great. The second kind of topic that we talked about was gas laws. And with gas laws, there's a couple different types of questions. One is just a conceptual question, such as this one. In this question, it says, consider 2 identical flasks, one containing 2 moles of O2 gas at 175 K. Now remember, mole is referring to the number of particles we have, right? And so 2 units of particles at 175K, and the other containing 2 moles of O2 at 425K. So what we see is that the moles is the same, okay? So we have the same number of particles in box 1 and box 2, but what changes is this one is at a much higher temperature, right? And so if the question then says, which of the following statements is true? Well, the first one says that the pressure is the same. Now, there's actually a couple different ways you could tackle multiple choice problems. What I would recommend with multiple choice problems generally is to have an idea before you go into the problems, looking at the problems, if at all possible. This way you can basically just, if you kind of know what you're looking for, you can weed out distractions. You can kind of take out the distractor answers is what we call them. And so that's always helpful. If you have no idea though, and you don't know what you're doing going into, then you can just kind of eliminate false answer choices so you can help yourself out. But before we read these answer choices, let's maybe consider, right? What's going to happen here, right? We know that PV is equal to nRT, right? And so, well, if PV is equal to nRT, right, the relationship between pressure and temperature, right, is going to be direct, right? So if temperature increases, right, then that's going to result in the pressure also increasing. We can also think back to our Can Crush as well as our little FET simulation that we did a CR on, right? In both of those, we also saw, hey, you heat up your container, the pressure increases, right? But also, here's another way, right? So in general, what we're seeing is that pressure, if temperature increases, pressure is going to increase. And so now we can go here and say, okay, well, A, the pressure is the same. No, that's not going to be true, right? If everything else is constant, but temperature is different, then no, pressure is not going to be the same, right? Okay, the rate at which the O2 molecules collide with the flask walls is higher in flask 1 than in flask 2. And if we think about that, right, we think here they're going slower, right? Here they're going faster. So is there going to be less collisions here? Yeah, right. We know that actually what's going to be the case is that in 2 there are going to be more collisions. And so this idea that there's going to be more collisions? No, that's not true, right? And another way you can think about it is remembering that, well, the definition of gas pressure is the number of collisions that occur. And so, or that's part of it, right? It's the pressure created by the collisions. And so, yeah, no, if pressure is higher in flask 2, it makes no sense that there's going to be less collisions in flask 2. Nope, that's not true. The average speed of the O2 molecules is lower in flask 1 than in flask 2. Is that true? Yeah, right. If there's less temperature really is correlated with speed of particles, right? And so, yeah, no, that's actually true. If the speed of the molecules in flask 2 is flask 1 is going to be much lower than the ones in flask 2. So that's true. Let's go see flask D, or let's see answer choice D to see if that's also true, just in case. So the average kinetic energy is the same. No, right? Kinetic energy, right, we know is speed. And so no, the average kinetic energy is not going to be the same. It's going to be much higher in 2. So no, it's C. Okay, so this brings me also to another point here, some other notes as mentioned in class, right? And so these are just some help for you guys. The first thing I mentioned where kinetic energy is equal to speed. So if it says the molecules have high kinetic energy, that means the molecules have a high speed or are moving fast. Okay, so kinetic energy is speed is kinetic energy. At least for chemistry. And so we can use that here, but also here's another thing, multiple choice help. Just because an answer choice is true doesn't mean it's correct, okay? So just because an answer choice is true does not mean it's correct. Use that when you're going over some of these multiple choice questions. That'll be helpful. But here we were able to go through process of elimination. Actually, all of the ones that were incorrect were false as well, so that was helpful. All right, cool. Let's go through these now, or at least a couple of them. Below I will list 2 variables to describe a gas using PV is equal to nRT. Tell me, are they directly or inversely related? Write an equation that would describe the relationship between the 2 in a before and after situation. And so basically, this is just me having you practice deriving equations, right? This was really my second hint here, right? Know how to get other formulas from a given formula. So let's do some practice here, right? Pressure and moles. What is the relationship between pressure and moles? And so, well, if we're given PV is equal to nRT, right, and pressure is P and moles is N, what we want to do is we take a look here and we're like, okay, is this direct or inverse? Direct or inverse, right? And what we know is that, well, if pressure increases, then moles must also increase because they're equal to each other, right? So the way you can kind of think about it is we need to have both of these sides be equal to one another. And so right now they're like this, right? They're both kind of the same amount. Now, if pressure increases, right, so we're basically kind of adding some amount here, you're going to have moles also increase, right? So that basically the left is the same as the right, okay? Do you see the equal sign, right? These two sides have to be equal to each other. We have to have this and this be equal to each other. So if pressure increases, moles also increases. Now, of course, we're not thinking about RT or V, right? Because right now we're only dealing with pressure and moles, okay? And so, yeah, if pressure increases, moles has to increase. Conversely, also, if pressure decreases, moles has to increase. Sorry, if pressure decreases, moles also has to decrease, okay? So, as a result, what we know is that they're directly related. And so, the form of a directly related equation for two variables is going to be the ratio, right? P1N1 is equal to P2 N2. Or you could have also flipped it, right? N1P1 is equal to N2 over P2, right? And so, yeah, either of those would be good. And so if we go to pressure and temperature, right? Again, PV is equal to nRT. Pressure is P, temperature is T, P and T. Again, same situation. If P increases, T must increase since they're on opposite sides. These are directly related. And therefore, P1, T1 is equal to P2, T2. Now, another thing you could note, right, is that you can also technically just pull this equation, right, from here, where, again, these are just your given equations on another piece of paper, right, but P1, T1, P2, T2, right, I mean, it's the same thing, right? If we just take out V, basically, right, you also have that same equation, right? There are multiple ways to do this, but yeah, I'm just showing you one way. Cool, okay, so now let's go on to pressure and volume. Well, PV is equal to nRT, right? And pressure is P, volume is V. And so here we have them, oh, they're actually on the same side of the equation, right? They're kind of on the same side overall. And so what we're seeing is that, well, kind of drawing a picture again, what we're saying is basically, hey, if you have like on the right side something, and on the left side you have something, if you were to increase, I'm trying to draw them about the same size. Right, so if you have two things roughly the same size, right, and if P was to increase, right, we're not dealing with anything on the right side, so we can't increase the amount on the right this time. The only thing we can do to make sure that these two are still the same size is actually to take away from the other thing that's involved here, right? So to take away from V, right? And then hopefully these are about the same amount of area at this point. Area, so if I'm the box shaded in like this, they'd be roughly the same amount. And so what we see is that actually if pressure increases, to keep the two sides equal to one another, volume would actually have to decrease. And so what we say is that, right, this is the opposite. We're going to say they're actually inversely related. And so therefore, P1 V1 is equal to P2 V2, right? This is what the form of that equation is going to take on. It's not going to be a ratio, right? It's going to be them multiplied together. Now, do note, you could also technically write like V1 P1 is equal to V2 P2, right? Like it doesn't matter, though we're really used to writing it like this. So, but it doesn't matter, right? You get the point anyways. Cool, okay. Now temperature and volume, right? Again, let's think about it. PV is equal to nRT. T and V. And so let's see, we got V, T. These are on opposite sides, right? So again, we can see it's directly related. And so therefore, it's going to be V1 T1 is equal to V2 T2. Or you could do opposite. T1 over V1 is equal to T2 over V2. It doesn't matter. Cool. Okay. Now, this next one, temperature in moles, right? T N PV is equal to nRT. Now, what we would say is, well, T is here, N is here, and so, ooh, they're actually inversely related, and so therefore T1 N1, right, is equal to T2 N2, right? But I'll be honest, this actually isn't true. This is theoretical. It's not true. Someone actually asked me today this in class, and so that's why I put this on here. I mean, if you think about it, temperature and moles actually aren't related to one another. It's actually a little bit more complex than this, more than we'll get into in a introductory science high school chemistry class. But basically, actually, moles is what we would call a fixed parameter here. It's not exactly the same thing as R, where R is a constant, but moles is more of a fixed parameter. It's not a freely floating variable. In fact, it's basically, how do I put it? You could define another variable A in terms of R and N, and you're probably losing me at this point. My point is, this is kind of a trick question, which I would never give you on a exam. But yeah, temperature and moles actually aren't related to one another. Yeah. So I'm just going to cross that off, and I'll explain in my answer key why more later. But yeah, it's that you actually can't have that relationship. Fun facts: if you were confused by that, and you're like, "What the heck?" Don't worry about it. That was just some kids got that and appreciated it, and if you didn't, that's totally okay. You're still great. Cool. Okay. Temperature and pressure now. Temperature and pressure. This actually is a legitimate one. PV is equal to nRT. T and P. That's got to be direct, right? And so this is direct. And so therefore, P1 T1 is equal to P2 T2. Nice. And then volume and pressure, I'm going to put that here. PV is equal to nRT. Volume, oh, wait, shoot. This is the same thing as above here, right? So yeah, I'm actually going to cross this off then for the answer key. Yeah, I mean, that's just this one, right? So let's not worry about it. Cool. Okay, good to know. Before I post this for you guys, I'll change that as well. Cool. Okay, so then here we got some, equations, which we're going to use. Basically, I'll do one of them for you guys. I want you guys to note this. Whenever you're doing these, go through my little gas problem solving template, right? If you ever get stuck, right? First, just write out, okay, what did I get from this problem? What equation should I use? Draw it out, plug it in, and then give me your final answer, right? So let's kind of go through that, right? What do we get? Well, 22.5 liters of gas is at this pressure, okay? It's at 748 mmHg. And so it's like, okay, well, that's my volume. It's first 22.5 liters. My pressure is 748 mmHg. Cool, okay. But then it's compressed to 725 mmHg. And so what we're seeing is that there is kind of like a pressure, there's a second pressure, right? There's a bit of a pressure before and a pressure after, okay? So we're kind of in a before and after situation. Now this is a constant temperature, so basically saying, hey, don't worry about temperature. Temperature doesn't change. And so what is the new volume? And so, yeah, this question is asking, hey, what happens to the volume afterwards? So before we're like this, afterwards we're like this. So now we know what we have. We gathered up what we have. And so if we have V and P, we're going to have to use the V and P equation, right? And so we can look up here, right, because we've already gotten it, right? Pressure and volume are going to be related like this. We already worked through the logic, so I'm just going to apply it now here. P1 V1 is equal to P2 V2. Okay, so that's kind of my second step. Okay, that's the equation I should use. My third step now is just draw it out so I can visualize it a bit, right? Basically what we're saying is, hey, we used to have 22.5 liters, right? And, a lot of movement of gases. And the pressure, right, was 748. Now what happens later is that the pressure actually decreases, right? Pressure 2, maybe I should do it here. Pressure 2 is equal to 725 mmHg. And so what I'm thinking is, obviously what must have happened is the volume must have gotten bigger, right? Basically, what I'm already thinking in my head is like, this must have gotten bigger, more roomier. That's why the pressure decreased. Now, let's test out that hypothesis, right? We can now go on to the fourth step, plugging in, right? But do you see how by drawing it out, I'm basically able to start visualizing, making sense of what I'm doing? And so now plugging it in, right? 22.5 liters. Please do include your units, otherwise you will be quite sad. 725 mmHg and V2. Cool. Okay, so I want to get V2, so I'm going to divide by 725 mmHg on both sides. And now I can get rid of these two guys. mmHg will cancel, and what I'm going to get is V2 is equal to, let me grab my calculator real quick. What we're going to get is 22.5 times 748 divided by 725. We get 23.2 liters. All right, and then remember your sig figs. 3 sig figs, 3 sig figs, 3 sig figs, so we can have 3 sig figs at the end. Nice, right? And so that's how you do that one. And just for the sake of length of video, we're already at 21 minutes, right? So I won't do these ones as well. Do note that for this one, right, we're going to use PV is equal to nRT, because this isn't a before and after. It's saying how many moles, right? So that's N. We don't know N. It's saying, hey, that's our volume. This is our pressure. And this is our temperature. Do note that you got to convert that to Ks. But, yeah, right? So we're given all those. If we can figure out R, then we can just plug it to here, right? This isn't a before and after situation. This is, hey, I give you a bunch of variables, figure out N. And so what you would have to do is solve for N, right? So you would have PV divided by RT is equal to N. And you can just plug in, and yeah, you get the right answer. But cool. Okay, let's go on now to elements, compounds, mixtures. That's the next big topic that we learned, right? And so for this one, I accidentally forgot to delete the answer. But right, what we're seeing is that there's this type of particle as well as this type of particle. 2 different types of particles. That's a mixture. You don't have to explain it, right? But just for the answer key, 2 types of particles, right? So it's going to be a mixture. All right. How about this one, right? It's only one type of particle, only one type of atom, and therefore this has to be an element, right? Yeah, because we only have one type of atom. How about here? You might be considering saying compound, but remember, a compound is when you have 2 different types of atoms put together, right? 2 different types of atoms, and so this actually is still going to be an element, right? This is going to be a molecule of an element, but it's an element nonetheless. It's not a compound, okay? Whereas this guy, right, when we have 2 different types of atoms stuck together, this will be indeed a compound. Here, if you see, right, we have the Al atom as well as the Cl atom, right? This is two types of atoms stuck together, so this will also be a compound. Here we have 2 pure substances, 2 different types of particles, just in the same area, and, right? And so that tips us off. It tells us, hey, that's a mixture. And then lastly here, we only have 1 type of atom. This must be an element. Cool. Okay. Coming into the home stretch, we have the law of conservation of matter. Do the following reactions follow the law of conservation of matter? Why or why not? And remember, the law of conservation of matter simply says that matter can neither be created nor destroyed in a chemical reaction. We're simply moving around the atoms and elements that we have. And so basically what you want to do here is to see, okay, what do I have on the left? What do I have on the right? And based on that, do we follow the law of conservation of matter? And so for me, what I do is I kind of think, okay, well, I have C, H, and O here. And here I have C, H, and O as well. Cool, okay, so far so good. But how many C's do I have? I have 1. How many H's? 4. How many O's? Well, do note, okay, this is O2, but there's 2 O2s, so we have 4 O atoms, okay? It's all about the atoms, okay? So let me write that down for you guys. Look at the atoms. All right, so 1, 4, 4, and then here we have 1. We have 2 times 2, right? So if you have two H2Os, it's going to be 4 H's. Then we have 2, 3 oxygens, right? Oh, no, sorry, I messed up. Not 3, right? Because we have 2 oxygens, and then 2 times 1, so 2 here, 2 here, so we have 4 oxygens, right? And so if you at all get confused by this, just draw it out, right? So you can say, okay, well, I have C, H, right? And then O2, I have 2 of them, right? And then here we have CO2, CO, and then we have 2 H2O. And here we have our H's and our O's, right? And so then you can just count it, right? 1 C, 1, 2, 3, 4 hydrogens, 1, 2, 3, 4 O's right on the left. And on the right, we have 1 carbon, 1, 2, 3, 4 oxygens, and 1, 2, 3, 4 hydrogens, right? And so another way to do it is to draw it either way, right? What you can see is we do have the same on the left and the right. And so this does follow the law of conservation of matter. So I'm just gonna put a yes. We have the same amount of each type of atom on left in the reactants as we do on right in the products, right? And so therefore, yeah, we do follow the law of conservation of matter. All right, going on to the second one, right? H2SO4 plus Zn yields ZnSO4, right? What we see is, hey, well, we have H, O, S, and Zn as our 4 here. And then we have Zn, S, and O. So Zn, S, and O. Now, right off the bat, right, what can you see? Right, we have 3 types of atoms here, but we have 4 here, right? And so what we're seeing is we're missing hydrogen. Somehow, some way, we just don't have hydrogen on the right side. And so this doesn't follow the law of conservation of matter, right? Because you can't destroy hydrogen. Where'd the hydrogen go? This doesn't make sense. It doesn't follow the law of conservation of matter. And so this is no. We had H on the left in the reactants, but don't on the right in the products. And so, no, does not work. Cool. Okay, so then we get to one of our last topics, law of conservation of mass, right? That's the same idea as the law of conservation of matter. It just simply says, though, that in a chemical reaction, mass, right? Because mass is a quality of matter, right? It's a property of matter. And so, yeah, this follows as well that you must have the same amount of matter on left and right. You must have the same mass on left and right. And so consider the following reaction: HCl plus NaOH yields NaCl and H2O. If we have 2.5 grams of HCl and 3.3 grams of NaOH to start, and we form 4.3 grams of H2O, how many grams of NaCl must we form? Right, and so basically what this is saying is, hey, you must have the same on the left grams as things on the right grams. And so if we have 2.5 grams here, and 3.3 grams here, and 4.3 grams here, right, what we see is that 2.5 plus 3.3, we have 5.8 grams of reactant, right? So we must have 5.8 grams of product, right? Now, of those 5.8 grams, 4.3 grams are H2O, and so therefore the remaining only 1.5 grams is of NaCl, right? And the way to do that is 5.8 minus 4.3 grams, right, is equal to 1.5, right? And so there you go. That's that one. let's now skip on to here. For each of the following, determine which elements are present and how many of each element there are. Also give the meaning of the symbol in parentheses, right? And so basically this is just kind of an application of what we were doing in 2.5 when we were drawing out, as well as taking a look at the law of conservation of matter, as well as what we were doing in our lab, but kind of just formalizing it here. Basically, what you want to do is say, okay, if we have mg here, right, and there's no subscript, therefore there's only one mg, right? And if there is a 2 here, right, that 2 around the parentheses is being applied to both O and H, right? So there's going to be 2 O's and 2 H's. Now the last thing this is saying is give the meaning of the symbol AQ, right? That's aqueous. Okay, so just be able to give the name. Nice. All right, then here, right, if we have a 2 next to the H, right, that means that you have 2 hydrogens. If you have, well, we have nothing next to the S, right? And so it's only gonna be 1 S, and then we have a 4 next to the O, and so it's gonna be 4O. Again, that's aqueous. And so there you go. I'm not sure if I'm spelling it right, but again, spelling is fine, don't worry about it. All right, here we have nothing next to Ca, so it's just 1 Ca. No numbers at least, right? And then we have NO3, all of that in a parentheses of 2, and so we have 2 N's, right? 2 N's, and we have 2 O3s. If you have 2 O3s, then you must have 6 O's, right? Again, you can kind of think about it and draw it out. It's like, okay, I have 1 NO3, then 2 NO3s, I have 1, 2, 3, 4, 5, 6 O's. There you go. This is S, that's solid. Nice. Now here we have 3 Ks. There's nothing around this parentheses, and so we just have 1 P, and we have 4 O's. Nice. And again, this is solid. Here we have 4 Cs, 10 H's. The L means liquid. And then lastly here we have 1 C, 2 O, and the G means gas. And so there you go. Hopefully that helps you guys out. Hopefully it walks you through how to do every type of these questions. I know I didn't walk you through like that one, right? Or like these, but again, based on the other ones that I did, hopefully this makes a lot of sense. Those also make sense as well. So you guys got it. Please don't freak out. You guys are great. You guys are quite bright, more so than you think. And so take a deep breath, just work hard, do some practice. Don't freak out if you don't get it at first. That's chemistry, that's learning. If it was easy, you shouldn't come to school then, right? That's not the point of it. It's for you to learn. And you guys are learning. You guys have been doing great. You guys have been improving a lot. So yeah, keep learning with that. Proud of you guys. Also, please enjoy your weekend. Please only study for a little bit of time, for a couple hours, and then go on and enjoy your weekend, man. Have fun. Let me know if you have any questions. Also happy to help you guys out on Tuesday, since our celebration of learning isn't until Thursday. So let me know if you need any help. I'll see you guys then.